introduce our last speaker of the day, Ursula Molter from Universidad de Buenos Aires. We'll talk about basis of exponentials and multitiles, please.
Thank you very much, and thank you for organizing this very, very interesting program. I wish it were in person and not just via Zoom. We are all getting to know each other by the little squares on the screen. And I have to say, I'm a little bit embarrassed to talk about basis of exponentials after the very beautiful talk of Alexander Olewski yesterday. So I was happy that I already had the title slightly changed, because I'm partially answering one of the small questions that he left us at the end of his talk. So I want to say that the end of this work is a collaboration with Catherine Hare from the University of Waterloo and Carlos Cabrelli, who has been working on this for much longer. So we were basing ourselves on the work of Ilona Agora, Jorge Antesana, Carlos, and Diana Carvajal. And we were, of course, inspired by many other people, Kolumtsakis, Grebstad, Lev, Nisan, Olewski, Ulanovsky, and for sure I'm forgetting some of the papers we read during our journey in this subject. So what I want to recall is the basic question: given a set B in Rd, can we find a discrete set gamma such that the exponentials with frequencies in gamma are an orthonormal or Riesz basis for L2 of B, the functions supported in B? If yes, we will call gamma an orthonormal or Riesz spectrum. If we don't say anything, we mean orthonormal. Otherwise, I will add the word Riesz, because my talk is mainly about the Riesz spectrum today. In general, one can ask if for a bounded, compactly supported Borel measure, can we find a spectrum for L2 of mu? This is a question that is very close to my heart. Today, I'm not going to talk about this. Obviously, we all know in the moment when somebody asks about the existence of a basis of orthogonal exponentials, we remember Fuglede, who in 1974 poses the famous conjecture: a set omega of finite measure admits an orthogonal spectrum if and only if omega tiles Rd by translations. This conjecture was, of course, proved false in general by Terry Tao. However, if we rephrase the question, well, it becomes actually true. A set omega of finite measure admits an orthogonal spectrum gamma with gamma a lattice if and only if omega tiles Rd by translations on gamma star, where gamma star is the dual lattice. This was already proved by Fuglede, but if by this conjecture, by this theorem, I'm sorry, if we have the result that if omega does not tile by translations on a lattice, it will not admit an orthogonal spectrum, which is a lattice. So can omega admit a spectrum that is not a lattice? Well, as Alexander Olewski mentioned yesterday, in general, this question is open. Fuglede proved that a triangle or the disk are not spectral. And so one immediately says, okay, if there are sets which are not spectral, meaning that they don't have an orthogonal basis of exponentials, could they have a respaces of exponential? So does, for example, L2 of D admit a respaces of exponentials? Does there exist any set such that L2 of S does not admit a respectrum? Well, yesterday we learned that in fact there does exist such a set S. I had to add this slide because until yesterday I didn't know that such a set in fact existed. So he told us, and we are all waiting for the paper, that there does exist a set S such that L2 of S does not admit any basis of exponentials. So let me go a little bit back to the theorem of Fuglede. Fuglede proves that if a set is tiles by translations on a lattice, then it will admit a spectrum on the dual lattice, an orthogonal spectrum. However, if it does not tile the lattice, then it will not have an orthogonal spectrum. Notice this set, which I pictured here, the black dots, which we have here, are the lattice, and the blue set union the red set union the green set is my set omega. Obviously, it doesn't tile because we realize that immediately it has some overlap if I translate. However, if I compute the characteristic of the translations of this set omega on all the lattice, all the black dots, the sum of this is constantly 3. If it were to tile, the constant would be 1, always, almost everywhere. So it does not tile, so we cannot expect to have a spectrum on a lattice. This set is particular. It's called a 3-tile in general, referring to my title. Multi-tiles, I'm never sure if I pronounce this correctly, but I say multi-tiles. A set omega in RD, I take K in N and lambda a lattice. We say that omega is a K tile for lambda, so what is written here, if the sum of the translations of this set omega is equal to K for almost every omega in RD. For example, the set which we had before is a 3-tile, which is bounded. And now I want to draw your attention to another set, which will pop up later. So I take the interval 0, 1 on the real line. And now I take a copy of the interval 0, 1, split up into all the dyadic intervals which make up the whole interval 0, 1, and translate them onto the whole real line. So to each dyadic interval, I add an integer. So this is the 0, 1/2, this is the 1/2, 3/4, this is the 3/4, 9/8, and so on. I couldn't have more precision because it's getting very little. So this is a two-tile. Let me just stop here. But this two-tile is unbounded, right? Because it is spread out on the whole line. So there is a theorem, which is the one I'm referring to today. If we have a bounded set omega, then the following two conditions are equivalent. There exists a lattice lambda such that omega is a k-tile for lambda, and there exist k reals in Rd such that the exponentials on the translations of the lattice gamma, which in fact is the dual of the or lattice for which omega translates. So these exponentials are a respaces for L2 of omega. So we have a theorem which says again, if omega is a k-tile for a lattice lambda, then we have a respectrum for omega of the form k translates of the dual lattice lambda. Well, this theorem is not new. It was proven by Grabstad and Leff in 2014 with some additional conditions on the boundary of omega, which have been taken away by Kolountzakis, who also presented a nicer proof in 2015. And the other implication was done by Agora, Antesana, and Cabrelli in 2015. So we do have something which is almost a version of Fuglede's theorem, because we have a set k tiles the space if and only if it has a, well, not a orthogonal basis, but it has a respaces of exponentials. And these exponentials are not just arbitrary ones, they are k translations of the dual lattice. In fact, this can be proven for general LCA groups, but this is not what I'm interested in now. But I have to say, Fuglede's theorem is for general sets. This one is for bounded sets. In fact, for unbounded sets, it is not necessarily true. I am going back to the example I had before, I mentioned it before, so you are familiar when I introduce it formally. So as I told you, I split up the interval in all the dyadic intervals. I consider B1 the set 0, 1, and B2 the union of all the dyadic intervals translated by L. So this is, as I told you before, a two-tile. If you translate it by the integers, you see that every point is covered exactly twice. And one can, in fact, prove that there is no translations of the dual lattice of R, which is R, such that, I'm sorry, this dual lattice of Z, such that the exponentials on the translations of these two lattices are Rie spaces. And the proof of this is because of a beautiful theorem which says that something, the exponentials, are Rie spaces for L2 of omega if and only if a certain matrix is invertible, but not only invertible, but that the determinant is bounded away from zero on a set omega, which is a fundamental domain for the lattice, in this case, Z. And I will write down which is the matrix because I know everybody wants to see this. So my matrix, which depends obviously on the choice of A, which is A1 and A2. We have 2 points here. These are the translations of the lattice. And lambda of omega is given an omega. What did we know? That our set big omega is a two-tile. So for every omega, I have exactly 2 lambdas in big lambda, such that omega plus lambda is in big omega. Bad choice of letters, nice to write, but bad to say. And so for each omega, I have exactly 2 numbers, lambda 1 and lambda 2. And so I get a 2 by 2 matrix. Well, and now I need that the determinant of this matrix has to be bounded away from zero. So the question arises, which are the conditions on omega such that there exists k, a1 and ak, and lambda such that the determinant of this matrix is bounded away from zero if omega maybe tiles, multi-tiles is bounded. We don't, this is exactly what I'm going to address now. So together with a student of Carlos, they were trying to see if they could find an unbounded set which still is a k-tile, yes, but is unbounded and still has a Rie spaces of exponentials. And they knew what they have to prove is that this third determinant is bounded away from zero. Well, so they came up with a definition. They extend the notion to sets omega, which are what they call admissible. And admissible means that all the k translates of a given omega are, we can find a large number n such that all these inner products are different modulus n. And I will put an example because here a picture is better than many words. Look at any bounded set. Obviously, any bounded set. If I translate a point from the lattice. Oh, and I want to see how many points fall inside this bounded set. Well, since the set is bounded, obviously there are only finitely many for any point. And so if I take an n larger than the biggest one, well, then this set will be admissible. Well, how about this one? Is this counterexample, which I had before, admissible? Well, no, because lambda 1, I mean the first translate of any point of omega by z will be, if I don't translate it at all, if I leave it in 0, recall that we have to look at the omegas in a fundamental domain of this lattice, and this is the 0, 1 in the case of the integers. So the first translate for any element omega of, I'm sorry, I wanted to point, if my set omega is the union of the 0, 1 and the translates, the first element lambda is 0, and the second one is j, because for every interval in the 0, 1, it belongs to one of the dyadics, and this dyadic is some way translated in my picture. So this means that for any n, these two lambdas will not be congruent mod n. So unfortunately, this example does not fall into the correct category of those sets for which Cabrelli and Carvajal could prove that there exist free spaces. We know that this two-tile does not have any free spaces, not any, I'm sorry, structured free spaces, because one can prove that the determinant of this that matrix is not bounded away from 0. So how did this set is not admissible, and they were proving. So I just wanted to point out in this slide that the condition of admissibility is still only sufficient. Remember that the condition of bounded was sufficient for the part to guarantee the existence of a structured, I will call a respaces, which is the translate of a lattice, a structured respaces. The condition of being admissible is only sufficient. And so the idea, again, to show a counterexample, of course, that they have already an example of a set that was not admissible, and that's why there could not be a respaces, but to see that there could be a set which is not admissible with a respaces, well, what they do is they spread out the intervals in a slightly different way and still find an example of a set which is not not admissible, but does have a structured respaces. Exactly, a respaces translated by two elements, because this is a two-tile. We are still in the same idea of taking omega, the union of the translates of the dyadic intervals. So here is an idea of the proof. You want to see when this matrix is close to some matrix which you take that has a big determinant, so they translate the intervals by elements which are spread out in a way that the determinant is always bigger than the determinant of a fixed matrix minus epsilon, and therefore this determinant is positive. And so even though this set is not admissible, they find a respacing. So admissibility does not seem to be the right condition. So here I put the graphic. We have the big universe of K-tiles. And then we have the K-tiles which admit a structured respaces. We know that this is strictly smaller because of the first example and the second example, because there are sets which have structured respaces, but there are K-tiles which do not have structured respaces. Among those that have structured respaces, some are admissible, and among those which are admissible are the bounded. Okay, so we visited Catherine Hare in Waterloo, and we tried to see if we could characterize, giving a necessary and sufficient condition for a K-tile to have a structured respaces. Unfortunately, this was not very simple, but it was very interesting how different areas from mathematics come together. So we had to we tried, let me say how we started. We looked at the two counter examples. This guy here, which had been proven before that it does not have a respaces. This one, which has a respaces, but what we found is there was something which was common to the counterexamples. So we had to look at the Bohr compactification, which for many in this audience is probably well known. I just write down what it is. I'm not going to go into the proofs, but the idea is we compactificate. We will look at the Bohr compactification of the lattice for which our set is a tile. So remember that if I have a lattice, I have, if G is a locally compact abelian Hausdorff group, you can think of a lattice. We take its Pontryagin dual. Now I take the discrete topology of this Pontryagin dual and take the dual of this, the Pontryagin dual of this group with a discrete topology. Well, we know that the dual of a discrete group is compact. So we have a set gamma tilde, which is larger than G, which is the theorem of Bohr, which is compact. And just because I may have time, the compact open topology on G tilde, which is called the Bohr topology, the neighborhoods of a point x naught in G tilde are all the x's in G tilde such that if we look at this difference, x gamma minus x naught in gamma is less than epsilon, so this is a neighborhood in epsilon, and for every gamma in a compact set in the discrete topology of big gamma, and which is the big, so in fact we are looking at a finite number of gammas which I have to check. So this is what I say here. A neighborhood, in fact, are all those x in G tilde such that their distance to a given gamma I is less than epsilon for a finite number of k. So I pick any finite elements in my set gamma, the dual of G, and I have to check what happens if I take this. This notation means the gamma I in X, right? Because gammas are in the dual. So what I note this here, I made a mistake. This is this, so it will not be corrected, but you see it. And this has to be smaller than epsilon. So we can come to our theorem. We look at a set omega in Rd that is a k-tile for a lattice lambda, which has finite measure, but does not need to be bounded. For each omega in big omega, I look at the set lambda sub omega, which are the elements of my lattice, such that when I translate omega, it will meet lambda, it will meet big omega. So what I say is that omega plus lambda j of omega is in big omega, and I do this for all omega, little omegas in a fundamental domain of the lattice lambda. Right? It's the same idea than I had before. So if I call lambda tilde the Bohr compactification of lambda, for any k tuple in Rd, and for any character, k couple character, I mean a k couple, k characters. So he1, he k belongs to the dual to the k. So I can make the matrix M A P, which is just the evaluation of A1 up to AK. The first row evaluates P1 in A1, the second P2, and the last one Pk in all elements of A. Note that in the particular case that my P is one of the lambda omegas, which I had before, then we think of this, we can look at this P of A as the exponentials in with frequency A times lambda of omega. Well, so if our k tuple of elements is exactly lambda 1 to lambda k, where the lambda 1s and lambda k's are here, I think I went too far, are here, exactly those, then my matrix MAE is exactly the matrix I defined before, is the matrix of exponentials with frequencies A lambda of omega, which, recall, had to be, sorry, I wanted to say, this matrix for this particular choice has to have its determinant bounded away from 0. This was the theorem. Well, so here we come to the theorem. Given an A, remember, was A1, AK in RD. I take a character in lambda tilde, in the dual of the lattice to the K, and I take the closure of all the elements that appear when I evaluate omega. I take omega in a fundamental domain and look which lambdas of my lattice lambda k, when I translate them, which ones are those that hit my set omega, which was a k tile for RD. So the theorem says, and I give you time to look at it, it is equivalent to be a respaces of translations of the lattice gamma star, no, lambda star, where lambda is this lattice on which omega k tiles RD. So if I have a set which k tiles RD, and I have a set A1, AK in RD, then it is equivalent that the exponentials with frequencies on the translates of the lattice lambda star are a basis for omega, and that the intersection between this set, the set S sub A, which is those characters that make the determinant of this matrix 0. So this set SA has to have empty intersection with the closure in the Pontryagin, in the Bohr compactification of lambda tilde to the K, with the set of translates which hit omega. Well, this is the proof of this, or the idea for this came up after looking at what was failing in the previous counterexamples. So the good part is that we have a necessary and sufficient condition for a set omega that k tiles to check whether it will admit a respectrum with, if we are able to check if this intersection is empty? Well, I mean, we have to resort to the Bohr topology. The calculation is not easy, but at least we have a necessary insufficient condition. And so I wrote it here again. If omega is a k-tile for lambda, then omega admits a structured re-spaces if and only if there exists A1 up to AK in RD, such that the determinant of this matrix is not zero for all characters in D closure, in D, sorry, which is the closure of. I think I want to end here because I don't want to go into the proof. I know I ended early, but I hope you may have questions, and so I stop here.
Thank you very much, Ursula, for wonderful talk. Questions, comments, suggestions?
I think there is a question in the chat.
I don't see it.
No. I will stop sharing. If somebody has a question, I can come up again. So I guess I was too short. I could have given some of the proofs, but I didn't want to go into technical details.
Okay. Well, if there are no questions, let's thank Ursula again. And we